Hi students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as wave theory. Now last time we had seen how a polarizer works. Let's see the same concept again with two Nicol prisms. I have a Nicol prism here which is going to act as a polarizer. Let's keep another Nicol prism just next to it. This particular Nicol prism is called as the analyzer. Right? You have a ray of light entering. This is your ordinary light. Right? It is going to get doubly refracted. Right, one of which the ordinary light is going to be absorbed here. This is the ordinary light that is going to get absorbed. The extraordinary light will pass through and will pass through straight. So the light that will come out from the polarizer is going to be the extraordinary light. Right? Now if I keep another Nicol prism, in that case, since the Nicol prism allows the extraordinary light to pass through, this particular extraordinary light will pass through it. Right? And you will have intensity maximum intensity of light coming out from here. The maximum intensity of light coming out from here. So today we are going to see why do I need that second Nicol prism and why is it called as an analyzer. So let's see the working of Nicol prism as an analyzer. Nicol prism as an analyzer. Now, light emerging from the polarizer, light emerging from polarizer is made to fall on another Nicol prism This is another Nicol prism A called analyzer. Right? Now, such that now initially what I'm going to do is I'm going to keep the principal section of the polarizer and analyzer parallel to each other. What is principal section? See guys, remember you had cut the Nicol prism where you had cut it and you had joined it using that Canada balsam. That is your principal section. So initially I'm going to keep the principal section of the polarizer and analyzer parallel to each other. If the principal section of the polarizer and analyzer are kept parallel to each other, if the principal section of the polarizer and analyzer are kept parallel to each other, then the intensity of light emerging beam from the analyzer is maximum. Right? So in that case, now if I rotate the analyzer, if the principal section of the analyzer is rotated, if principal section, if A is rotated till its principal section becomes perpendicular to the principal section of the polarizer, principal section of the polarizer, no light comes out from the analyzer. No light comes out from the analyzer. Right? So long as the two principal sections are parallel to each other, you will be having light. You will have light coming out from the analyzer. But if the principal section of the analyzer is made perpendicular to that of the polarizer, there will be no light coming out from the analyzer. Right? This is because this why. This is because in this case the light vibrations. In this case, light vibrations in A are perpendicular to the principal section of A. In simple language, the light that was coming out from the polarizer was polarized in a particular direction. So it will pass through the analyzer if the principal section of the analyzer is in the same direction. If I make it perpendicular, then the direction in which light is polarized and the direction in which the analyzer would allow light to pass are not the same, and therefore no light would pass through the analyzer. Right? So this is how you use a Nichol prism as an analyzer. So in order to find out whether the light is polarized or no, initially you pass a beam of light and keep the principal section of the polarizer and the analyzer parallel to each other. Right? Light would come out. Then rotate the principal section of the analyzer by 90 degree. Right? If light does not come out, that means the light was plain polarized light. If light still comes out from the analyzer, that means it is ordinary light. That's how you use the analyzer. Fine. Next, what are the drawbacks of Nichol prism? Let's see the drawback of Nichol prism. Its cost is very high due to the rare availability of large, flawless calcite crystal. Cost is very high. Right? Next, due to the extraordinary ray passing obliquely through, the emergent ray is always displaced a little to one side. Remember, you have refraction taking place. Now because of the refraction, the extraordinary ray will not pass straight. It will pass through one side. That means, see guys, if this is my prism, I should have had the extraordinary light coming out from here. Instead of that, it will come out from one corner. Right? So you will say that due to the extraordinary ray, due to the extraordinary ray passing obliquely through it, the emergent ray is always displaced. The emergent ray is always displaced a little to one side. A little to one side. Right? Next, the effective field of the view is limited. Now remember, the ordinary light gets total internal reflected and the extraordinary light passes through because of that critical angle. So the effective view is 12 degrees upwards and 12 degrees downwards. So the effective view, the effective angle of incidence that I could keep is very, very less. The effective field of view is limited. Right? Next, I cannot use a Nichol prism for UV light as Canada Balsam absorbs UV light. It cannot be used or ultraviolet light as Canada balsam absorbs UV. Right? Next, the light that comes out from a Nicol prism is not uniformly plane polarized. Right? Light is not uniformly plane polarized. Right? Those are the drawbacks of Nicol prism. Right? Where do I use Nicol prism? Uses of Nicol prism. Nicol prism is used to produce a plane polarized light and functions as a polarizer. Produces a plane polarized light and functions as a polarizer. Right? Second, it can also be used as an analyzer to find a plane polarized light. Can also be used as an analyzer. So these are the uses of Nicol prism. Next, let's move on to something else now. Let's see what do we understand by polarize. Right? Now there are certain crystals which doubly refract a ray of light. They have a property of absorbing one of the doubly refracted beams to a greater extent than the other. There are certain crystals of doubly refracting class which have a property of absorbing one of the doubly refracted ray, the doubly refracted ray to a greater extent than the other. Greater extent than other. That means you would have a crystal, some crystal, right? As soon as the light enters it, it would doubly refract the ray of light. Then it would allow that light to pass through, and the intensity of this will be more, and the intensity of the other light will be less. So it will absorb one of the doubly refracted beam of light more than the other one. And that is an inherent property of certain material. It is an inherent property of certain crystals. Okay, do you understand this? Now this, the crystals that show such property are, the crystals showing such property are termed as dichoric, and this phenomena is called as dichorism. Right? Crystals showing such property are called dichoric, and the phenomena is called dichorism. Right? It is also referred to by some authors as a phenomena of selective absorption. Fine, do we get this in here? Now, amongst the crystals, there is one particular crystal which is called as tourmaline crystal. Now, tourmaline crystal is a dichroic crystal. That means A, it will doubly refract a ray of light. Then it will also selectively absorb one beam of light more than the other. Right? So, tourmaline crystal is a dichroic crystal. Right? Now this particular crystal has a property that it absorbs the ordinary ray completely. Tourmaline crystal has a property that it absorbs the ordinary ray completely. Right? Hence, the light that comes out from a tourmaline crystal is an extraordinary ray which is only partly absorbed. So, this light emerging from a tourmaline crystal therefore is a plane polarized light, because the ordinary light has been completely absorbed. It's only the extraordinary ray that has passed through. I can say hence light coming out is plane polarized. So light that comes out from a tourmaline crystal is a plane polarized light. Now this phenomena of selective absorption is used for the construction of polarides. Polarides were made in the year 1852, right, by an English physicist who was trying to produce a synthetic dichroic crystal, right. He came up with a crystal of iodosulfate and quinine, and he called that crystal as herpetite, right. Herpetite had a property that it could transmit plane polarized light of all colors and wavelength, right. These crystals were small, unstable, and cannot even bear a small strain. So the first attempt to make polarides was made in 1852, right. So in 1852, let's see the history. In 1852, you had an English physicist by the name Herpetite. Successfully produced a synthetic dichroic crystal of iodosulfate and called it iodosulfate of quinine, called herpetite. Right, this was the first attempt. Now, this particular crystal could transmit plane polarized light. Plane polarized light of all colors. It could transmit plane polarized light of all colors and wavelengths. But the problem with this crystal was that it could not bear even a small amount of strain. The crystals were small, unstable, and cannot bear a small strain. First attempt to make a polaride, right? Then in 1934, you had another scientist by the name E. Lance. He developed a large size polarizing film using special optic techniques. What he did was he embedded this herpetite in a cellulose acetate medium. Now a cellulose acetate medium is a viscous medium. So he put those crystals in a viscous medium with their optic axis parallel. So all the crystals had their optic axis parallel, as a result of which the layer of crystal was mounted then on a glass sheet so that the crystals are not spoiled, right? What you got then was a polarizing sheet, right? And this particular sheet was called as a Polaroid. The crystals would pass a plane polarized light. Since it was made up of herpetite, it was synthetically produced, they exhibited dichroism, they exhibited selective absorption, and as they were mounted in viscous sheet and then on a glass sheet, they could bear a large amount of strain. That's how a Polaroid was made. Fine, do you get this thing clear? So in 1934, you had a scientist by the name E.H. Land. That was 1852, this is 1934. In 1934, E.H. Land embedded herpetite. He embedded herpetite in cellulose acetate with their optic axis parallel, and mounted it between glass sheets. Mounted it between glass sheets, right? So that the crystals don't get spoiled. And this was called as a polarizer sheet. This was called as a polarizer sheet. Right? And these were then called as Polaroids. Fine, do we get this thing here? So that's how Polaroids were made. Now, when we have Polaroids nowadays that you have are further classified. They are classified into H Polaroids and K Polaroids. Right? Polaroids which are prepared by stretching a thin film of polyvinyl alcohol, which is stretched about 3 to 8 times its original length by subjecting it to a very large strain, are called as H Polaroids. Right? Due to this stretching, the complex molecules orient themselves automatically with their axis parallel to each other. Right? And these are called as H Polaroids. In H Polaroids, you have a long chain of molecules where the optic axes are parallel to each other. So, the electric field of the incident light parallel to the molecule easily gets absorbed, and the absorption is due to the large electrical conductivity of iodine molecules that are used in it. So it has a greater degree of absorption. So an H Polaroid is more effective than a herpetite Polaroid. It absorbs, it gives you almost 100% polarization. Right? The next thing that was developed was K Polaroids. K Polaroids was discovered by Land and Rogers, and that was again prepared by stretching polyvinyl alcohol film, but it was stretched in the presence of hydrochloric acid. Now, as we know, if it is an acid, that means it is going to be a dehydrating agent. So, that would, due to the presence of hydrochloric acid, there was a slight darkening of the film. Right? At this stage, because of this dehydration, the film became extremely dichroic and became very, very stable. Right? And these films were then called as K Polaroids, and it is the K Polaroids which are used on automobiles. Right? Because they do not get bleached in sunlight. Fine, do we get this thing clear? So thus you have two different kinds of Polaroids. You have H Polaroids and K Polaroids. H Polaroids are prepared by stretching a polyvinyl alcohol film of between 3 to 8 times under the presence of a large strain. The optic axis automatically arrange themselves parallel to each other, and they are then further impregnated with iodine crystals to make them highly dichoric. They have very high amount of polarization. They give you almost 100% polarization. And the next one was K-polarize, where you polarize the given polyvinyl alcohol sheet in the presence of hydrochloric acid. That will produce slight darkening of the film, and that will also make the film extremely dichoric and very stable, which would not be bleached in sunlight, right? So do you understand the two different types of polarides? Where do we use polarides? Polarides are used in sunglasses, one of the basic application of them. Remember, a polarized sheet or a polarized sunglass is different than a colored sunglass. Okay. They are also used to view three-dimensional pictures. In order to see a 3D movie, that particular sheet that you have is a polarized sheet, right? Then because of their low cost, they are used to produce and detect plain polarized light in lab. They are used on window planes. Then they are used to study optical properties of metal. They are used to improve the color contrast of old paintings. When you have all these old paintings revived, how do they revive it? By using polarized sheets on them. That produces a better contrast on them, right? And that's it. So those are the applications of polarides, right? With this chapter is over. Now the numericals are remaining. We'll do that in the next lecture. Let's stop here for the day. Thank you very much.